Okay, so just now we saw that, if we were to use Chebyshev to control the sum of independent random variables, in particular in this example where we take this matrix A and we try to control this infinity norm, this wasn't enough, right? It didn't give us anything interesting. I mean, you might say, I didn't say in the first part of this lecture, but you might say, okay, that's because maybe here we actually always get n. But if you think about it, that would be strange, right? Because for you to get actually that the value of this is n, you would need x to completely line up with one of the rows of A, right? And there's sort of exponentially many points, possible points in the hypercube. So you would expect that you need exponentially many rows of A, not just n. So now we're actually going to get something. We're going to prove an inequality that's much more of that style, right? We're going to get an exponential dependency on the deviations. So what we're going to prove is Hoeffding's inequality. So let me write it. Theorem. So this is Hoeffding's. And so what does Hoeffding say? It says that now here they don't even have to be IID. They just have to be independent. So let x1, xn be independent random variables. They are bounded. So xi is smaller or equal than ai, almost surely. And say means 0. Expectation of xi is 0. Okay, it's true for all I. Then we're going to get that the probability, right, that the sum is large, right, as mean 0. The sum will also have mean 0, of course. Right, and we're going to do it in spectral norm. We bound both the sort of the upper tail and the lower tail at the same time. Right, and basically, because we're bounding two tails, we're essentially union bounding over both, so we get this 2. And then exponential of minus t squared over 2 the sum of the AIs, of the AKs. And so we'll see this is a lot stronger. In particular, we're actually going to focus even in the proof, because you'll see the proof is exactly the same in general, just allows me to have less parameters. Let's focus. Okay, so let's focus on the case where the AKs are all equal to A, right? They're all the same. Okay, so now if we do that, and we get, say, let's try to plug in a T that makes this thing small, right? Let's say that we take, okay, so let's say that we take T to be square root of 2, some constant U, okay, log n, and then A. Okay, so the product of these four things. So what do we get, right? If we take, right, we get the probability that the sum, the xk's absolute value is bigger or equal than, right? Right, okay, this is bigger or equal. If we get that the sum is bigger or equal than, okay, let's write this out. So square root 2 UA log n. Oh, I'm missing I missed an n, right? Okay, so let's do this all. So UA U UA n log n. Okay, so 2 UA n log n. Smaller or equal than, and now, okay, I pick this so that, we would get like all the cancellation we need up here. So I get minus t squared, so I get minus the square of this, so the 2 cancels with the 2. This is, okay, this needs to be a square, of course. So right, when I take the square of this, the 2 cancels with this 2, the a square, the na square cancels with the na square that comes from here, and so we get minus u log n. So what is this? This is 2n to the minus u. And so if we think in the example before, if we take u to be, say, 2, or even 1 plus epsilon, if we pick u to be 1 plus epsilon, and we plug it above, right, what would we get? we would get that the probability, right? This xk is there plus or minus 1. So a here is 1, right? And so if you plugged it in here, right, what would we get? We would get that this probability smaller or equal than n times 2, okay, times the exponential of, right? Uh, sorry. Okay, we would pick t. We'd have to pick t to be, square root 2 1 plus epsilon, right? N log n. Okay, and then we would get that the probability is smaller or equal than n times 2 times n to the minus 1 plus epsilon. Right? So this would be equal to 2n to the minus epsilon, or 1 over, so I can write this as 2 over n to the epsilon. So for any epsilon positive, the probability that the infinity norm of ax is bigger or equal than this constant is now smaller or equal than a polynomial in n, right? 2 over n to some epsilon, right? So you see that now this is very meaningful, right? Because now I'm saying that we actually get a control on the infinity norm of this object to be, we get the control that it's with very high probability, with probability 2 to the n over n, 2 over n to the epsilon, is at most 2n log n plus some multiplicative 1 plus epsilon, right? Or times some multiplicative factor of 1 plus epsilon. Right, and this is quite remarkable, right? So, the typical size of each one of these entries of this vector is n, and what we get by taking the maximum over n things, or is root n, and what we get for taking the maximum over n things is an extra root log n. Right? So as you can see, this inequality is a lot more powerful. Right? So now let's prove it. Okay, so let's do the proof. Okay, so let's take, right, so this is like, right, comment, just so that you see the power of this inequality. So let's do the proof. Okay, and again, we'll do the case on when a case is equal to a for all k, just because, the proof is a bit, I don't have to carry around as many, as much notation, and you'll see the proof is exactly the same for the general case. Okay, so again, so the idea will be to use Chernoff, right? To use Chernoff method. Okay, so we're going to use Chernoff method. What we're going to do, we're going to see, so we're going to understand the probability of the sum being too big, right? And then we could do the same thing for minus xk's and understand the probability that the sum is too negative, and then we just union bound for both, and that's how we would get this 2. So we're going to prove just the bound on one side and get to the exponential without the 2. Right, so the probability that the sum, k from 1 to n of xk, is bigger or equal than t. Right, so this is now smaller or equal than, this is now smaller or equal than, I take the exponential, I'm using the Chernoff method, so this is the probability that e to the, or exp of lambda sum, k from 1 to n xk, smaller or equal than exp lambda t. Okay, now I use Markov, right? So now we use Markov, right? Same thing as what we've been doing. Oh, this is bigger or equal, of course. Okay, so now we use Markov. So what does Markov give us? Right, and we're going to optimize over lambda later, right? So we take some lambda bigger equal than 0. Some lambda bigger than 0. And now Markov says that is smaller or equal than the expected value of the exponential of lambda k from 1 to n. Exponential, right, times the exponential of minus lambda t. Right, and now we have to understand the moment generating function of this. Okay, but this is now the expected value of the exponential of a sum, right? So what is this equal to? Okay, let's move the other term here. It's a bit nicer. Okay, now what do we have here? We have expected value, right? The exponential of a sum is the product of the exponential. So we get k from 1 to n of exponential lambda xn or xk. These are all xk's. Okay, but now they're independent, right? So here we use independence. They're independent, so the expected value of the product is the same thing as the product of expectation. This exponential of minus lambda t. Now I get the product k from 1 to n of the expected value of the exponential of lambda xk. So now what we have to do is we have to understand this quantity, right? We need to bound this. Okay, we could of course bound it, since xk is always smaller than a, we could bound it by exponential of lambda a, but it's not quite enough, right? And in particular, by doing that, we wouldn't be using the fact that the random variable is centered, and this is of course very important, right? We need to use this. So now we need to bound, right? Need to bound exponential e to the lambda x for x always smaller than a and centered. Okay, so this is what we need to do. Okay, so how do we do this? And we do this with convexity. Right, so f of x equals e to the lambda x is convex. So what does it mean, right? Let's draw a picture. Okay, we have a, we have minus a, and we have some x here. Now let's say that I have e to the lambda a and e to the minus lambda a, right, or lambda minus a. The fact that it's convex means the function f of x is somewhere, will do something like this, right? But it's always below the line between them, right? This here is always above this here, right? That's what convexity tells us. So in particular, we can write that now as an equation, right? E to the lambda x is smaller or equal than, so let's get an equation for the line, a plus x over 2a e to the lambda x plus a minus x over 2a e to the minus lambda x, lambda a. Okay, this is just convexity. Okay, but what does this mean? It does, right? The expected value of e to the lambda x is smaller or equal than the expected value of this, right? But the expected value of x is 0, so these terms go away. So really all I have, the only thing that survives, right? I have maybe I should write it down, right? The expected value of x, 2a, e to the lambda a plus a minus expected value of x, 2a, e to the minus lambda a. Right, but the expected value of x is 0, so I just get 1/2 e to the lambda a plus e to the minus lambda a. Right, this has a name. This is the hyperbolic cosine of lambda a. Okay, now some calculus. Calculus, basically, you have to use Taylor's approximation. It's not so hard to see that cosine, hyperbolic cosine of lambda a, is smaller or equal than e to the lambda a square over 2. Try it. Okay, so try it. Try to show it. Right, it's just calculus here. So what does this mean? This means now I plug everything together. What do I get? I get that the probability, right, of the sum of the xk's being bigger or equal than t is smaller or equal than e to the minus lambda t times the product from k from 1 to n of this exponential. But this is smaller or equal than e to the lambda a squared over 2, right? And if I had different ak's, I would just have to keep track of them here. Okay, but what is this? This is all the same, so it's n times. So all I have is e to the minus lambda t, right? E to the n lambda a square over 2. Okay, so what is this equal to? It's equal to a minus lambda t plus n a square lambda square. Same game as before. Now pick optimal lambda. What is optimal lambda? We just have to take derivatives. Right, and so optimal lambda, like lambda opt, right? We just need to take the derivative. We just need to take the derivative of this and set it to 0. There was an over 2 missing. Okay, and if we do this, then lambda opt is equal to t over n over a square. Okay, so now we plug that in. So we get that the probability of sum of xk bigger or equal than t is smaller or equal than e to the minus, okay, and so what we get here, lambda t times this is minus t squared over na squared, plus, now I get t squared, right? Then the n squared, the 1 over n squared times the n becomes n, right? And the a square times the 1 over a to the 4 becomes an a square, and then there's a 2. Same thing as before, right? So now I have minus something plus half of it, so this is e to the minus t square over 2n a square, right? Which is exactly what we wanted to show, right? Remember what we saw here, right? It's exactly what we wanted to show, right? Right, here I get n a square rather than the sum of the ak squares, but you know the argument would just be the same exactly. Okay, and now to get to, now do the same, right? You would have to do the same for, probability of minus exponential of xk in the order of some t, and then you would do, and then union bound, right? Union bound for, you need to union bound for on both union bound, and that's how the factor of 2 comes about, right? Because I'm controlling here the two the two tails, right? Because I have the absolute value, I have to prove that it's not too big and it's not too negative. Okay? That's where this 2 comes from. Okay, so this is a very powerful inequality, as we saw in that example. And in fact, I mean, so I'll show you in a second an example of this inequality, like an application of it. But first, let me show you another inequality that sometimes improves over this one. Is actually one that we're going to use a lot. Okay. So this inequality has okay. Actually, before we do this, let's see a use. Let's see example like example of application. Okay, we already saw one, but right, we already saw an example of an application when we did right when we just saw that Chebyshev wasn't giving us what we needed for controlling the infinity norm of that matrix. Let's see another example. Okay, remember when we said, right, like a couple lecture ago, we said most of the volume of the cube lies in its corners. Okay, so you said that most of the volume of the cube lies in its corners. Okay, and we saw this because we computed volumes of the ball and so on. I'm going to do this now in a much, much simpler way. Right? So take x, a random variable, and you'll see, right, we don't need to do any exact computations to do this calculation now. Right, before we need to understand the volume of the sphere and so on, you'll see now this comes out really, really simply. Okay, let's say that x is drawn uniformly in the cube of, say, radius 1. Okay, I mean, we could take radius a half, any radius, the calculation doesn't change. Let's do radius 1 just to have less things to keep track of. Okay, so it's uniform in the cube of radius 1. And now what we want to understand is the probability that this random point x, so the probability that this random point x happens to also lie in the ball of radius 1. And we're going to show that this probability goes to 0 very quickly as d goes to infinity. Okay, so how do we do this? So first of all, let's understand a bit better this uniform distribution over the cube. Right, if I have a uniform distribution over the cube, then this means that x1 all the way to xd, right, they're independent. And they're uniform over minus 1, 1. Right, because the cube is a product, the uniform distribution on the cube is a product measure. Right, this is not true in the ball, of course. Right, in the ball, the coordinates are independent. Right, but in the cube, they are. Right, the cube is just products. Right, it's Cartesian products of minus 1 and 1. Okay, now the probability of it being in the ball is the same thing as the probability, right, that the L2 norm of x is smaller or equal than 1 or smaller than 1, right? So in particular, it's the probability that the sum of the xk squares, k from 1 to n, is smaller than 1. Okay. But now we can try to use, concentration inequalities, right? We have to understand what is the expected value of sum of xk squares, right? Now these random variables are independent, right? And so maybe we can, use concentration inequality. So in order to use concentration inequalities, we need to have something that is, a random variable minus its mean. So let's make that show up. right? So we have the probability, we can write sum of xk square minus the expected value of the sum of xk squares, right? K from 1 to n. This is smaller than 1 minus the expected value of xk squared, okay? Okay, so far so good. So now we need to compute this expected value, right? So of course I can move the expected value inside the xk's, right? These, means and this can be swapped, right? Because expectation is linear. So let's compute the expected value, right? So we need to compute expected value of xk squared, right? But this we can do just by, just by the integrals, right? This is 1/2 the size of the cube minus 1 to 1. The integral of 1 over to 1 of x squared, right, dx. Okay, but what is this? This is just 1/2. And now I get, right, what is the antiderivative of this is just x cubed over 3. So I get 1 over 3, right, cubed, but that doesn't matter, minus 1 cubed over 3, right? But what is this? This is just 1/3, 1/2, 2/3, right? It's just 1/3. Okay, so the expected value is 1/3. Great, so let's see what this gives us. So we get the probability that x is in the ball is equal to the probability that, sum of the xk's, right? I can write like this, for example, right? So that now they are, centered. This is just the same thing as what was above. 1 to n is smaller than 1 minus, I have summed this over d times, I have d over 3. But now we can use Hoeffding. So to use Hoeffding, what do I need? I need to notice that xk squared, right, minus expected value of xk squared is always smaller or equal than something, almost surely. But what is this something? Let's think about it. So this variable is between minus 1 and 1, so the square is between 0 and 1, and I subtract 1/3. So it's between now minus 1/3 and 2/3. So this is smaller or equal than 2/3. Great. So I can use Hoeffding, right? And I'm only controlling all of the tails, so I don't even have this extra 1/2. So can use Hoeffding, and it says it is smaller or equal than, I get exponential of minus t squared, right? So I get minus, what is t? Is 1 over d cubed squared over, and what do I get? 2 times n is d times a squared, right? 2/3 squared. Okay, now let's just stare at this expression for a second, right? When I open this square, I'm going to get a term in constant term, a term in d, and a term in d square. Of course, the term in d square is the one that's big. The other ones don't really matter. And the term in d square is going to have a 1 over 9, right? And then here I have a d that's going to cancel that d. And I'm going to have here, this will be like 8 over 9. The 9s are going to cancel, and I'm going to get something like the leading order thing is minus d over 8. Okay, and so I'm going to just take, the number after to make sure that it's smaller, so I don't have to worry about it. Let's say that this is smaller than d over 9. Okay, so the probability, right? The probability is extremely small, right? It's going to 0 as d goes to infinity. And now we did this without having to compute, volumes of spheres or anything like that. And of course, if you needed the ball to be, if you wanted to say, oh, but the ball, what about the ball of radius 10? Right? If I was to do the ball of radius 10 here, instead of 1, I would get 10. The only difference is that here, instead of 1, I would get a 10, right? But it wouldn't matter. The leading order term would still be of the same size, right? So you saw we could understand something about high-dimensional geometry using probability, I would argue, in a much, much simpler way. Okay, and now let me just show you another inequality. So let me motivate one weakness of.
So let's say I had an issue with the audio, so I had to switch this, but maybe I'll repeat this again. So I'm going to show a weakness of Bernstein. So let's take random variables, R1, Rn, independent, in particular IID, right? And they will be the following distribution. So Rk is distributed in the following way. Let's say they're -1 with probability p, over 2. They're 0 with probability 1 minus p, and they're -1 with probability p over 2. Okay, and let's think of, in our head, let's think of p very small. And now let's say we want to understand the sum of our k's as k goes from 1 to n. clearly, I mean intuitively, clearly the bigger P is, the smaller P is. If P is very, very small, the smallest this should be, right? Intuitively, this should get smaller. This should be smaller, or should concentrate better, should be smaller for small p, right? And but Hoeffding doesn't see that, right? Because for Hoeffding, we have to have RK smaller or equal than something, almost surely, then this something must be 1, right? It doesn't matter that it attends this maximum not so often, right? Hoeffding doesn't see this, right? But Hoeffding doesn't see this. And so there is an inequality that sees this, and this is this is Bernstein's inequality. Okay, so I won't prove this inequality because this inequality, the proof is very, very similar to Hoeffding. You should look it in the book, or try to prove it. Try to prove it yourself to make sure that you really understood, how the proof of Hoeffding works. But Bernstein's inequality says the following. Okay? So this is one of the most useful inequalities for sums of independent random variables. It's the one I use all the time, right? And most people working in these things, the one they use most of the times. Okay, so I have a random variable xk. They need to be centered. Okay, so let's state everything, right? So x1 through xn independent, right? Let's say all the xk's are smaller than almost surely smaller or equal than some a, almost surely, and crucially, takes into account the variance of the random variables. Let's say that this is equal to sigma square. Okay, and the point is that it's taking into account another ingredient, that Hoeffding. And in particular, if you look at the variance of Rk, this is p, right? If you look at the variance, the expected value of one of these Rk square, this is p, right? So it's seeing p, while Hoeffding could have never seen it. It says the probability that the sum of xk's k from 1 to n is bigger than some t. This is smaller or equal than 2, and now it's exponential of minus t squared. And now, crucially, instead of a square, it has a sigma square here. Right? So it depends on the variance, not the maximum. So it sees if the spread gets smaller, right? It would have a p there rather than a 1. You should try it. Try to understand what control you would get for the random variables Rk. Right? If you use Hoeffding, you would get this with a 1. And if you use Bernstein here, this becomes p. So as p is smaller, you get a better control, right? But of course, we need the a does still make an appearance, right? When p is too small, you stop being able to control with p alone in this way, and the bound you get is this. Okay? But crucially, this one doesn't depend on n, right? It's sort of controlling, the fact that one of them might be very large. Okay, so this is extremely useful, this inequality. Okay, so you should try to control the value for these RKs using this inequality. And the proof of it, okay, so I won't show the proof, you should look in the book. But basically, the proof of it is by realizing, right? So when you use the moment generating function, really we're controlling at the same time all of the moments of xk, right? And I mean, at least intuitively, and if you go down in the proof more than just intuitively, you're sort of bounding, you can bound all the moments of xk by just a to the k, because the variables are always between minus a and a, so of course x to the k is between I, can be at most in absolute value a to the k. But now you have a control in the variance, so at least the second moment you have a better control. But you also have a better control of other moments, right? If you can control the fourth moment, you can just control by saying, well, it's at most sigma squared times a squared. Right? And so if you now use that knowledge and try to plug it in the proof of Hoeffding, you essentially get the proof of this. Right? So try it first, and then look in the book, try to prove it. Okay. All right. Thank you.